Hello and welcome to the Web Application Hacking and Security 102 lecture. My name is Dr. Owen Redwood, and this course is the Offensive Computer Security 2.0 courseware provided by hackallthethings.com. Today's lecture will go over a quick ethics reminder back from lecture 1. We'll go over the OWASP top 10 with respect to server-side attacks, and then we'll go into various details and examples on several types of server-side attack categories, ending with more complicated examples of SQL injection. So, the reminder is that the primary difference between legal hacking and illegal hacking is permission. If you do not have permission to perform those activities or any activities in question on any given server, do not do it. Again, you have to have permission from someone authorized to give such permission. Some intern is not going to cut it. System administrator or chief security officer or CEO or etc. have to sign off on these activities, and this is the standard way that penetration testing happens, that they solicit penetration tests from companies that employ hackers to do these things, and there's legal paperwork involved explaining the scope of the penetration test and what is not allowed. In other words, enumerating the permissions of the pen test. So, you should not take any of the topics of this lecture and perform them on someone else's server without having permission. However, there are plenty of avenues for you to still practice these techniques, such as capture the flag games and offline war games that have been set up in such a way that permission is explicitly granted, or these challenges you can run yourself in a virtual machine. Again, if you do not have permission to do techniques covered in this lecture especially, do not do them. So, web application security covers a lot of complicated areas that interact in complex ways, such as user authentication, session management, session tracking, user information such as personally identifiable information, protecting it and storing it, checking it and communicating it, and especially over encrypted channels, interaction with databases between the server-side scripts, the web page, the web application server itself, and various other servers that are acting together to deliver content and websites. So, in order to formally explain what is vulnerable and how and what the impact is, there's a good methodology that's here on this slide that is proposed by OWASP and is titled The Formal Approach to Vulnerability Assessment in Web Application Security. And it goes through the potential threat agents, the attack vectors they may leverage, security weaknesses that enable these attack vectors or may impact them, security controls that may or may not be enabled, and which ones should be enabled to, say, plug these weaknesses and vulnerabilities. Now, if it was exploited, what would the technical impacts be? And finally, what might the business impact be overall? Because in the end, certain types of hacks are not a big deal, but other types of hacks can be really bad for business in some cases. OWASP, which stands for the Open Web Application Security Project, is put together every 3 years a categorization of the top trends in terms of hacking against both web users as well as web servers. They change in priority from year to year, and they're ranked simply by how common they are. And A1 means that injection here is the most common, and it is in decreasing order. So the second most common vulnerability type is broken authentication mechanisms and broken session management. Then comes third is cross-site scripting. Then after that, insecure direct object references. Next is security misconfiguration, which is incredibly common and is often a default vulnerability in many content management systems and web server frameworks, as well as sensitive data exposure. Missing function level access controls is effectively admin functions and actions aren't sufficiently protected. And similar to that is cross-site request forgery, which typically attacks that same feature, or rather the admin functions. Next is using known vulnerable components such as plugins for, say, a WordPress CMS or other plugins for known CMSs, as well as unvalidated redirects and forwards, or allowing them. So we'll go down this list, and again, we're focusing on the server-side attacks. We've already covered cross-site scripting, and in turn, cross-site request forgery. So server-side attacks come in many styles outside of the OWASP category, and includes binary exploitation, which we've covered some of this so far. Binary exploitation of web servers has declined over the years as they've become more secure. It used to be much more common to find exploits for web servers such as Apache in the wild. This is much more rare nowadays. And web exploitation, which is, again, web application hacking. And finally, there are obviously other styles involving social engineering, which can target admins, physical attacks, and targeting data centers, supply chain, and etc. So, broken authentication and session management, which is very, very common, is a total no-brainer. It basically involves a insufficient protection or effort on part of the developers and simply just allowing cookies and session IDs to be sent over plain HTTP, not using any form of strict transport security as we covered in the previous lecture, allowing these cookies and session IDs to be exposed, and they can be hijacked by users who have man-in-the-middle privileges or capabilities, or some form of eavesdropping ability on the victim's network. Again, this can be used to target a server in general, as admins are users. So this is considered under server-side attacks mainly because it's specific to a given website. That website has to be misconfigured in such a way or insufficiently defended in such a way to specifically allow this for its users. Now, this can be used to access various privileged features and actions of, say, admin accounts or developer or editor accounts, or in other words, non-standard user accounts, and this can have a great impact on the website, its business, etc. So the formal way to test for this vulnerability is to create a user account or create accounts for all different user types, however many they may be. And for each one, test whether or not you can do all of the activities that an admin can do. And in general, here are some examples. Transfer funds, approve other users, approve content, delete content, add more users, grant other permissions, and etc. And it is considered really bad practice to assume that these functions are controlled simply by restricting these links only to the admins and assuming that only admins will see links to these functions. This is very, very bad practice. And the defense to this form of vulnerability is to implement function level access control. So for each of these functions on your site, you must check the privileges and authentication of the user. Next category is security misconfiguration, which is very, very common. It's very simple and straightforward. It's just simply using known vulnerable components or not patching the components that you utilize or not managing them, using them in default configurations that are inherently insecure, or not configuring plugins and other components properly, which all boils down to the admins of the site did not read the manual. Some example attack vectors include attackers being able to get in through default account usernames and passwords, being able to access unused pages of the website, being able to attack unpatched vulnerabilities, being able to access unprotected files and directories, which is related to the next topic, insecure direct object referencing. Now, this has some overlap with security misconfiguration, and it occurs when developers of a website expose a reference to some internal object through a URL, form, or parameter. This may be a file, a directory, it may be database records, it may be keys, or etc. But in general, in these cases, it is usually common that an attacker can use this vulnerability to access other records or objects without authorization as well. This is also very similar to broken authentication and security misconfiguration. So let's go over some example. One example, given the four PHP statements, we'll go over them real quickly. The point of this is to illustrate that this line allows the user to authenticate simply based off their username, and to trust the user to tell you who they are is very bad practice. So the first statement here prepares a query to select all records from the database where the username is as given. The prepared statement here prepares this, and there's something else going on. You don't really need to know, it's not that relevant, but what's setting it up is to establish what the argument is. So argument 1 is going to be here, and the next statement here, p statement .set string, will set the first argument to be equal to the username parameter returned through the user's GET request, and nothing else. And it's simply expecting the user to, at least the cookie, to send its just username, and it uses that, which is bad because in this case the username object is directly exposed to the users, and this can be abused by sending any other user, and it will, academically speaking in this case, it will take that as authentication and allow whatever action was requested. So this one example falls into multiple categories, but the specific aspect of it that makes it insecure direct object referencing is the exposure of the username property here, which directly maps to the username property in the users table of the database. So in conclusion on this topic, the key difference between insecure direct objects referencing and broken authentication for, say, let's go back, for, say, functions, is that when a web developer exposes certain functions of a website, such as admin functions to interact with other users, approve, deny, reject, etc., these are considered broken authentication in terms of it should be an action or an object that only an admin or an authenticated user can interact with. Now, for insecure direct object referencing, it has less to do with authentication. It's simply that objects that are either directly stored in the backend or are used in some form of the logic are exposed, and attackers can manipulate them as such. Next, the area in which a vulnerability is both an insecure direct object reference as well as a broken authentication vulnerability is when the action to view the object should require some form of authentication, but it can be abused to bypass that requirement. And secondly, when the object is not limited to the identity of whoever is authenticating. In other words, The action that is insufficiently protected is to view objects. But the objects, furthermore, are not securely referenced. They're allowed to be directly indexed or accessed or addressed by the user. In such a case, it is both of these vulnerabilities. But I digress. Now, we haven't called SQL injection, we haven't covered it yet, but in general, whenever an object is insecurely referenced and exposed to the user in this manner, and it's an object that is stored in the database backend, those cases are likely also SQL injection vulnerability vectors. And we'll cover those in a few slides. We're just going over the easy stuff first as a warm-up. So, objects are really files on the file system, on the server that's hosting the web page, database records that shouldn't have been exposed, keys, other people's posts, other people's messages, other people's account information, and etc. Next, cross-site request forgery, or CSRF or XSRF, is a cross-site scripting derivative that specifically targets privileged or administrator users of a website. And we cover it here as a server-side attack because it really is often used to gain access or gain some form of code execution or persistence on a target website. And so some examples are an attacker will target an admin, inject a XSS attack that makes a forged request to perform some authenticated action on the website, such as transfer funds, approve users, delete content, add users, etc., change permissions. And the problem for attackers is this is often application specific or CMS specific. In other words, the content management system frameworks that the website may be using. And for defenders, the defenses are all existing cross-site scripting defenses, as well as for users using script blockers and other security plugins. So, to recap what client-side scripting is essentially either infecting a web page with some form of stored payload that is sent to the users or victims when they visit the web page or that corner of the web page and view that object or content that's been stored, which is then a malicious script that runs on the client's browser and may leak out other objects of the client's browser, such as cookies, session IDs, and etc. So CSRF works like this in that the injected script that's sent to the victim will instead interact directly with the web page to perform some malicious request with that victim's permissions. Now, so stored cross-site request forgery works like this. The attacker visits the web page and uploads some form of malicious CSRF script, waits or baits the victim into visiting, and upon the visit, the script will be injected into the victim's browser, and if they don't have a script blocker, it will run and perform evil administrator actions if that victim is an admin. This is stored SSS or CSRF. Reflected script injection, also known as non-persistent, is one that is injected into the traffic stream. This requires man-in-the-middle capabilities on admins, which is somewhat requires the attackers doxing or knowing where the admins live or having some capabilities on the networking nodes between the users and the server. So the attacker will simply man in the middle of the traffic for the users that visit, and for the intended victim will see, hey, it's the admin, will intercept all the HTTP requests and HTTP responses, and with the HTTP response, it will inject, after, say, the authentication has been performed, malicious script into the traffic stream. Now, the web page will never see this. It's not stored. This is called reflected. And then if the victim's browser allows the script to run and there's no script blocker, it will perform evil administrator actions. It's very straightforward stuff. So the two defenses are: one, use strict HTTPS everywhere, which helps prevent man-in-the-middle script injection. Do not accept, especially admin function requests, over plain HTTP if you can. That depends on your web server. Use a good certificate authority and good certs. Never do self-signing if you rely on HTTPS to protect your administrator functions, which should be pretty much everything. And finally, all XSS defenses will apply in this scenario, which are: one, never insert untrusted user input into, say, storage like database. Two, HTML escape everything before inserting user input into, say, HTML element to reply back. Three, attribute escape before inserting user input into HTML attribute values. 4, JavaScript escape before inserting user input into any JSON or JavaScript values. 5, CSS escape, and strictly validate if possible before inserting user input into style properties. Less common, but is still a very valid attack vector. 6, URL escape before inserting user data into HTML URL parameters. 7, sanitize HTML markup with libraries designed for the job. And 8, prevent DOM-based XSS if possible. There's a cheat sheet listed below for your reference. I'd be remiss not to cover the old topic of directory traversal. It is considered not in the top 10 anymore, and it's simply when you access a website, you try to navigate outside of, say, the public HTML folder that the website files are running in, and try to access files specific to that server, say the password file in the Etsy directory. The defense is simply to configure the web server to recursively filter, not just once, but recursively filter these meta characters .. and forward and backward slashes. This is essential. Here are some old examples. PHP BB3 in the past was vulnerable to their filters filtered out .. that combination. And the bypass to get around it would be to have .. So this middle .. gets filtered out, and then the remainder is concatenated together still to be .. left over, and that's passed to the web server or passed to the rest of the code running PHP to access a resource, and allowed for directory traversal and accessing files that shouldn't be accessed. Webmin was vulnerable to performing this with HTML encoding and so on. The next topic, before we get into SQL injection and some hands-on with that, is using known vulnerable components, which is very common and very straightforward. The main culprits really amount to using vulnerable CMS plugins, which I think the people that I know that do this would consider the vast majority of CMS plugins, such as WordPress plugins, do have potential backdoors or vulnerabilities in them, that if you decide to use these plugins, you then inherit these vulnerabilities and expose your website to attacks through the plugins that you may not otherwise have had. Anyways, so the next topic, the next category that I've seen having a huge impact is shopping cart frameworks. There are some very big shopping cart frameworks that do not handle vulnerability disclosures ethically. They ignore them, and they expose all their users to them. Web application firewalls are also increasingly becoming problematic in the sense that people who use them do not update them. They deploy them once, they don't check them, they don't keep them patched and up to date, or they don't update their signatures as needed. This makes the web application firewalls not only grow ineffective, but also possibly to become an additional attack vector. And we have in the 4th web application security lecture various techniques that work almost universally to bypass web application firewalls for binary exploitation techniques, but I digress. Additionally, a big culprit in this area is server-side scripting engines, such as using old PHP versions and etc., using unpatched kernels or web server applications, using unpatched databases, not patching or updating things like OpenSSL. There are still many websites on the internet that are vulnerable to Heartbleed attacks, and so on. The key takeaway is to update and patch your components on a regular basis. So, before we get into SQL injection, there's a lot of common overlaps with the areas that we've covered so far, and these will also overlap with SQL injection itself in many areas. So, we've covered broken authentication and session management, security misconfiguration, insecure direct object referencing, cross-site request forgery, using known vulnerable components, and the old-school directory traversal vulnerabilities. Finally, the number one category for web application vulnerabilities is SQL injection. Some people refer to it simply as injection. This is incorrect. As we have illustrated thus far, cross-site scripting can be done via injection, as well as other attacks. But I digress. It is better called and categorized as meta-character injection with other attacks, but we will cover that at the end. For now, SQL injection we will simply define as vulnerabilities in which attackers can insert or inject arbitrary database queries, statements, or commands into the application, and the application then insecurely passes them along to the database to run. It's very easy to exploit. It's very common in terms of prevalence, and it's moderate to highly difficult to detect depending on the injection vector, and the impact is almost always severe. What limits the impact are the existence of any database user permissions as well as segmentation of databases. The business impact is almost always significant. As we've covered in Lecture 1, the average cost per leaked database record ranges from $130 to $154 something per record. Typically, databases have thousands or tens of thousands of records or more, and the impact for a potential exposure, or rather a potential compromise via SQL injection, can sink entire businesses. So databases will typically include data like the authentication credentials, username, password, etc., session IDs for users, other personally identifiable information such as address, credit card details, payment details. It will contain the site configuration as well as permissions for users, access control settings. It will contain typically all of the site content outside of the HTML and server-side scripting files. It will contain the themes. It will contain messages between users of the site, and so on. Now, before we go into SQL injection, we will first cover some basics of SQL. SQL stands for Structured Query Language, and in general, we're going to cover just MySQL, which is Oracle's database language. And in general, to retrieve information with a SQL language, you use the select statement. You can select everything in a table by select star from table, where you give it the table name. Now, if you want to select only certain statements given by a conditional, you would do select star from table where, and then you give the condition. To update records in a table, you would use the update statement, and the where clause works exactly as you would think it does. To add new information to a table, you would use the insert statement. To delete information from a table, you would use the delete statement, and the delete statement also has the where clause as you would expect it. It works the same across all of them. Now, in general, in MySQL, the hyphen space sequence of characters will comment anything else that follows that block of characters in a SQL statement, which is a common technique for attackers, depending on the database language, to inject in comment characters or comment meta characters to get it to ignore the rest of the statement, such that it may select where X is the case in A, B, and C, and if you can get it to comment out B and C, then you may be able to select more records. But I digress. Let's not get too much into the injection aspect of it. So far, we need to cover the basics. Now, typically, all databases will support what are called subqueries, which allows database engines to nest queries, so a single query will return a table in itself, and you can operate a nested query or subquery on that, and you can do it recursively to any level of depth in general. And so we have a real simple example below. In general, you can select 1 or 2, and it will just return 1 or 2, and that's the same as saying print 1 or print 2, say in Python. So this is an example of a subquery, and nested subqueries are, in at least MySQL, identified by parentheses. So whatever goes in the parentheses would be a subquery in terms of order of operations. So these get executed first, and then the parent statement would run with whatever values are there. So again, this would equate to select star from documents where ID equals 1, because you're doing select 1, and that's going to get returned as simply 1 and assigned to be the right-hand side of the conditional. Now, the next topic we have to cover is the union clause. In general, if you want to combine the set of results from two queries, you would use the union clause. One requirement, however, is that the number of columns in each result set must match. If they do not match, or if you have an uneven number of columns between the two, then syntax errors will be generated. The fact that this generates syntax errors if it's not used correctly allows attackers, when there's a SQL injection vulnerability, to enumerate the columns of any given vector by trying to union it with the result set of that given query that they're injecting into with some other query on another table, usually some standard table. And so they'll guess 1 column, 2 columns, 3 columns, 4 columns, and etc. And every time they guess a number of columns that's incorrect, that doesn't match the original SQL query, it'll generate a syntax statement, or error rather. And so when it works, it'll give them results. But I digress. This is getting ahead of ourselves. 2 examples are listed before you. There's just a real simple approach to this. You have 2 queries, and you don't need to say select twice sometimes, but it depends on the database management system you are using. But for instance, you could do select column A, column B from table X, and then union with column 1 and column 2 from table Y. This is valid because they have a matching number of columns. Similarly, you could do select ID number, first name, and last name from all your customers, and then union that with select ID number, first name, and last name from all your employees. This will return the ID number, first name, and last name for all of your customers and employees as a distinct set. So there won't be any redundant rows or records. There's no requirement for the data type of the columns to have to match. The only requirement for the union clause is that the number of columns need to be equal. So next, we will cover toy architecture for the rest of the discussion. On the client side, you have a presentation tier, and this is the level that users will see from Internet Explorer, Firefox, and Chrome. All the content gets rendered, and that what they see is called the presentation tier. The browser will interact with the web servers via HTTP requests, and will get responses back as HTTP responses. On the server side, this is all architected to be handled by a logic tier, which handles these requests, so a web server plus typically a server-side scripting engine for like a language such as PHP, Python, Perl, Rails, etc. And in the back end, there will be a database. So this is split into the logic tier and the data tier, and they interact with SQL or database commands and statements. And so the database will be some database engine with some language and so on, and it'll be interacted with to save user objects, save values, updates, etc., retrieve records, update records, delete records, and so on. This interaction is done for all purposes of all stages of website interaction, from authentication to interaction to logging out, and etc. At least for proper session management, logout is often just handled as deleting the cookie. And this should all be handled on the back end. It should not be exposed to the user whatsoever. So, we'll go through a quick little demo of how this architecture would work. Say, I have a problem with my computer. I found my cat digging around inside, and I need to replace some parts. So I'd go to some online store, and I'd browse. I need a new processor, so I'd look for items that they're selling in the category of processors. Pretty straightforward. And so on the logic tier, that would translate to retrieving data from my search, my GET request, to it wants to select all the records from the product table where the category fits a processor. And so I'll get all the results for i7, i5, AMD, etc. And then the presentation tier on my side, on the client side, will look like this. Primary causes of SQL injection are commonly three things. A, the failure of the developer to properly implement parameterized statements, which there are libraries to facilitate it, and they often utilize them incorrectly or insufficiently. To do this correctly, you must systemically sanitize every variable of user input that you use for your web application. This means every variable from GET requests, POST requests, including POST form submissions, cookies, user agent data, and so on. Anything you get from the user you should not trust, and you should sanitize through parameterized statements if it ends up interacting in any shape or form with the backend database. Second, related cause of SQL injection when parameterized statements are used is an improper type handling. If the developer fails in some way to handle the type correctly and ends up implementing the parameterized statement incorrectly, this can introduce, theoretically, a SQL injection vulnerability. And third is a lack of output filtering and error filtering to deny attackers introspection on the backend database interaction. of your website. Now for the types of SQL injection, there are two main categories. There are in-band SQL injection vulnerabilities and out-of-band, which is also considered blind. For in-band, we're going to cover two main categories, and we'll have variations of each one of these. Append-based, which is also called union select SQL injection, and error-based. And a single SQL injection vector may match more than one vulnerability type here. Exploiting each of these cases will require different techniques, and so we'll dive in and cover some of these. For out-of-band and blind vectors, you are limited in what you will, in terms of an attacker, what an attacker will get from the web server when it's manipulating a variable that may be a SQL injection vector. You may be able to slightly vary the existing content in terms of what it responds with by ID and etc. Or you may only be able to force it to compute something on the back end and vary in its response in terms of the time delay it takes. That's a bit more nuanced, so we'll cover it last. Append-based SQL injection vulnerabilities occur when the vector allows for the injection and display of results of a added union clause. We covered the union clause earlier, where you can combine the results from two different tables or two different result sets as long as they have a matching number of columns. A common technique, since an existing result set that one may be injecting into may be very large, is to first and foremost attempt to truncate the original query, or the original query to 0 roles, either by having it evaluate to a false condition or some other invalid or false parameter. Second, to inject the selected selected query to union with, and such that it has a matching number of columns with the original query. And third, well, this should rather be, if applicable, the results that you extract will need to return the same number of rows that are expected from the application logic. It's not always going to be applicable, but if it expects 2 to 10 records and you only return 1, it may throw an error saying array element not existing or something similar in PHP or whatever language. And fourth and finally, the results of the injected query must be able to be displayed somewhere on the page, typically where the data would normally be. For error-based SQL injection vectors, this occurs when the vector allows for the verbose display of SQL error messages. Verbose enough to, in fact, call out what is going wrong and how or why, which allows you to inject, say, variables and data into those verbose statements. The goal for an attacker, if they're trying to extract data through an error-based vector, is to try to manipulate the error messages to return results through. There are several quick and easy ways to detect the presence of verbose errors, but we've listed a universal error-based SQL injection test string below that should work on MySQL, Microsoft SQL, PostgreSQL, and Oracle SQL databases, and to trigger a reliable syntax error for any data type. Now, to exploit append-based SQL injection vectors, error-based, hold on. There we go, we fixed it. To exploit error-based SQL injection vectors, it takes two steps. One, you have to test whether or not there are verbose SQL errors that will print out on the web page. And then two, use varying techniques to extract values through the error statements. The next category, out-of-band SQL injection vectors, encompasses both response content-based as well as response time-based, which are rather called partial blind and full blind SQL injection vectors. And these occur when the vector does not allow the direct extraction of data through the vector. Partial blind is when data returned by the application changes only to some minor extent. This may mean that it simply does not display in one instance while it displays in another, allowing you to ask at least binary questions and have some visual confirmation. On the other hand, completely blind vulnerabilities will not result in the change of the return data set in the page output, and therefore attackers discovered that if you inject sleep statements, you can ask queries and force the response of the query to be a timing-based vector, or rather factor. And by having it sleep for the amount of seconds per response allows you to extract data even when you can't see anything. Successfully exploiting both of these categories requires some degree of automation in your attack. For partial blind, the steps to reliably exploit, or the two techniques, are either binary enumeration or multi-bit extraction, which was originally published under the theory of pre-computation and multi-bit extraction, which is far superior in the sense it allows you to successfully extract multiple bits per query, whereas in binary enumeration you get 1 bit per query whether it's true or false. So again, these are partial blind vectors where you have some visual response from each SQL injection attack, and allows you to, over time, enumerate or extract large chunks of data from the backend database. Again, it's best when pen testing real systems, to do targeted requests and not try to extract entire databases, especially on production systems, as that's really going to piss your client off. Meanwhile, for fully blind SQL injection vectors, the exploit techniques are the same, but applied differently. For binary enumeration and multi-bit extraction, the results are both passed to a sleep call, such that if it's an integer result, it will cause the database to sleep for that number of seconds before returning. There is a maximum timeout, however, dictated by either the web server, the PHP server engine, or the SQL database itself. And whichever one times out first will be the upper limit. The lower limit is dictated by the network latency, and specifically the round-trip time to the target. Your minimum sleep step should be large enough to accommodate for any potential lag spikes, and you can determine that by pinging the server for, say, an hour and observing the round-trip time, or rather response time for the ping, and picking the maximum time and doubling it should suffice. Now, there are SQL injection vulnerabilities that occur in nested subqueries, and these often get misidentified or miscategorized. But when these occur, they are categorized as second-order SQL injection vulnerabilities, and they may still be a pen-based, error-based, partial blind, or full blind. An example is presented below. This is some PHP code, and it's assigning ID to be the result of select ID from user, where username equals, and then it's passing in the PHP variable for name, which is presumed to come from the user, and that is the SQL injection vector here. And then it saves that into ID, and then the next line of code, data, is assigned to the query result of select star from users where ID equals the PHP variable ID. Now, if one were to inject into the name query here and say truncate these results or alter them in some way, say with a union select, and replace it with a different ID or a different variable, it could then be used to inject into the next one, select star from users where ID equals this, either to simply just manipulate the ID or to perhaps do something else. Most commonly it'll be to manipulate the ID, say to make it instead an admin user, which is a valid SQL injection attack. Another scenario is when, say, in form submissions, users can store variables on the PHP or database side that can be later used to trigger a SQL injection vulnerability. For instance, if we assign name to be the result of this query, select username from users table, where ID is given by the ID. If the username, when the form was submitted and the account was created, was not properly sanitized or properly parameterized and includes a SQL injection query in it, in other words, a SQL injection, and then it is returned and assigned a name, and name is used in this later statement. Options is assigned to the query result of select star from user option where username equals name. This can be exploited as if it were an in-band, append-based or error-based SQL injection vulnerability, but this is, again, nested, and it's a second-order scenario. So, the general process for exploiting a secondary SQL injection vulnerability, or second order rather, is first crafting the secondary injection to exploit the specific vulnerability category, whether it is append-based, error-based, partial blind, or full blind. And then next, if applicable, finding a trigger which causes that secondary injection to be injected. This trigger is always going to be part of the vulnerable application, and sometimes is activated by the same page as the initial injection point that you're putting the secondary injection in. And in many cases, pen testers falsely classify partial blind injection vectors when they are instead very commonly vulnerable to in-band second-order injection, because they don't understand what the second-order nested query is. Therefore, they're not really able to sanely manipulate the content and append a union select query to it and get sane data out of it, because they can't really observe that they're affecting some, not direct query, but a nested subquery. And so, understanding this aspect of doing vulnerability analysis for SQL injection is a key skill that people need to bring to the table. And so, if you recognize that a vector is actually a second-order in-band injection, you can actually extract a lot. So we've covered the primary causes of SQL injection vulnerabilities, and we've covered the top-level categories, including second-order SQL injection vulnerabilities. Now, let's cover the formal methodology that you can use for approaching the general problem. Then we'll dive into specific details on exploiting each category, and then we'll end it with demos. So the first step is to identify all SQL injection attack vectors and know how to detect all types in terms of both in-band and out-of-band, as well as correctly detecting second-order vectors. Two is to explore the limitations of each SQL injection vector that you have discovered and determine whether it is error-based, union-based, partial or full blind, whether it is second order. Next, determine what filters may be in place for white space, for syntax characters, for other alphanumeric restrictions, what encoding, if you can detect that, it may be determined by the server response. 3, enumerate the allowed meta characters, which is, I just explained this. 4, enumerate and map the database tables. This is a standard process per database management system, so it takes some experimentation with each database you are working with, whether it's Oracle, Microsoft SQL, MySQL, Postgres, or etc. And finally, after you've mapped the database, you want to extract the data from it in a targeted manner. So there are a number of vulnerability scanners that can detect some categories of SQL injection, but most of them, as far as I know, do not detect all of them. Until now, we're releasing a framework that thoroughly checks for every single category, including second order instances, and will recursively check and detect. As far as I know, other scanners do not recursively scan for second order vulnerabilities, and when they do detect them, they are often miscategorized. This list was put together with moderate amount of public research and using existing categorization and classification of tool capabilities, and is provided for your reference. Now let's cover how to check in depth for all of these SQL injection vectors. The difficulty can vary wildly depending on the SQL injection vulnerability type, and other factors such as the target environment, configuration, and security may raise obstacles to discovering and assessing vulnerabilities here. Basic methodology for each at a high level is as follows. Append-based vectors, you want to test for whether or not you can inject union operations by altering where clause statements, as well as being able to see if you can truncate the original query's results, perhaps either by a limit clause or by manipulating the where clause condition to evaluate always to false. Next, for error-based testing, which is usually the first thing people test, which is totally fine, is to test for whether or not you can generate SQL syntax errors and other specific errors, especially if they're verbose. For out-of-band or blind response-based testing, you want to see whether or not you can inject Boolean statements to vary content response slightly to reveal some fact of the backend database content. And response-based time testing is seeing if you can inject sleep statements to vary the response time. And while we've talked about this so far multiple times, the first thing someone needs to be aware of when testing for SQL injection vectors is constraints and limits. And so when a vulnerability is discovered, one of the first things, as we've discussed, is to enumerate. Let's go back real quick. Number 3 here, enumerate the allowed meta characters. So syntax characters, whitespace, quotes, semicolons, and attempt to bypass, see what allows you to bypass filters. And so this part of the process is specifically called isolation stripping. And you can find multiple blog posts and discussions on isolation stripping steps, and it's effectively exhaustively testing for inputs for which meta characters are stripped away from the vector, one meta character at a time, and then keeping track of what is stripped so you don't accidentally mess up your testing if you're programming it by getting your queries filtered out or rejected or manipulated in some way by the filters. So the first thing, as I said, most people check for is whether or not the site will generate SQL syntax errors and return them to the user. And commonly they try to inject string terminator syntax characters like a tick or a double quote. And there are other string terminator characters allowed in different languages. They have different ASCII codes or Unicode codes, and it will depend on your character encoding on the web server. The other category that's most commonly checked for is integer based, and again, string terminator injection here is attempts to cause a syntax error by injecting string content into, or delimiter into, what is just a numerical value. But we've provided a universal error-based SQL injection test string below here. It's single tick, double quote, $, tilde, backtick, greater than, less than, bang, minus, capital L, semicolon, and then A. In our experience, this will reliably generate a syntax error if it exists, if the vulnerability exists, from both Postgres, MySQL, Microsoft SQL, and Oracle databases. Next, we need to cover the procedure for universally testing whether or not there is a SQL injection vulnerability in the parts of a where clause, so that we can determine whether or not you can do a union select injection or a append-based injection. So we want to first be able to truncate the original query's results to 0, and you can do this by manipulating the where clause if possible to evaluate to false. And so the general meta character sequence would be formatted like this. You have an escape sequence, white space, conditional operator, white space, comparison, query terminator, and some escape sequence. This is appended to the existing value of the target variable. You don't always have to have the target variable be blank and just have this. You can have some value and then this appended on the end, this meta character sequence, this tester. And note that escape characters do not apply for non-text based inputs. So in other words, they don't apply for integer or numerical values. So given this example domain, domain.tld, so domain.com/vulnerable.php ? ID equals 1, and let's say we're testing it. We would then append this test as such, and since it's a number, we're not appending the escape sequence, so it's just white space conditional operator, white space comparison, query terminator, and so on. So for this, it's just then ID equals 1 space and 1 equals 1, or and 1 equals 2, and you can enumerate as such. Very simple, very straightforward. If it allows you to do that, then you have a SQL injection vulnerability, definitely. So again, many of these characters may be filtered, so you have to work through that isolation stripping. So we're going to go in depth on options to try for isolation stripping and solving this equation. There are many options for single quote and double quote, as well as backtick. In different languages, I don't have them all enumerated, but there is another option when escape sequences are filtered, say by MySQL real escape string. if you have a backend database on a web server that's telling you that character encoding is used and it's not UTF-8, you can use, depending on the language that the user agent or web server response is telling you that the server is using, you may be able to find a multi-byte escape string to bypass non-recursive filters, such as just single instances of MySQL real escape string. And this is detailed in a blog post that we have titled Using Multi-Byte Characters to Nullify SQL Injection Sanitizing. We provide a proof of concept script on GitHub. You can check out our GitHub for other useful open source tools, and this tool will be useful for both pen testers as well as defenders to tell you what multi-byte characters you need to worry about that allow you to do escape filtering bypass. So effectively what that means is having a 2 or more byte character such that it's only treating it as a single byte, but the second byte, which is typically used for accents in kanji and Arabic and other character sets and alphabets, you can actually put valid escape characters or escape sequences such as the slash character, which is 05C in ASCII. And what it will do is it will allow you to bypass actual escape sequences, such that if you put this right before, if you put one of these character sequences, here's the 05C, 01A. If you put 01A, 05C before, say, your single quote, double quote, or your other escape character, MySQL is going to come in, this is all passed through MySQL real escape strings, is going to put in a escape character, so a slash, a backslash right before it, and when it gets passed to the database, if it's allowed to recognize them as single byte characters, it's going to see a slash slash, then the string terminator. So the slash that MySQL just put in will just be escaped with this method, allowing the bypass of that filter, and then it'll interpret the quote or double quote character, allowing the termination of that variable. But I digress. So, moving on. Yes, there are multiple multi-byte character encodings that are vulnerable or offer this form of bypass, including Big 5, Hong Kong Big 5 supplementary character set, CP932, CP950, GB18030, GBK, Johab, and Shift JIS, which are, if you look over all of them, these are all Japanese, Chinese, and Korean character sets, interestingly enough. So, to enumerate white space in this equation, there are actually many options other than just space and tab. So this is an example. One could copy paste this for reference, and again, in isolation stripping, you just want to test one thing at a time. You can test these all at once or test them individually, but you're testing for whether or not white space meta characters here are being stripped. And so the overall query is just going to be something, and you're injecting and null is null. I've bolded them and translated it up here. You can also do and null is not null, It really doesn't matter. But what should be noted is that use of so many syntax characters in a single request, all these percents, may trigger some IDS flags. Let's see. So for the other ones, they're straightforward. You have conditional operators, parentheses, mathematical operators, comparison operators, as well as syntax bare words, which usually have some universality to them in SQL databases. These should be present in every SQL database. And again, we've covered this universal test string. And we put out a blog post on a solid methodology for detecting blind SQL injection vectors and testing them and fingerprinting them, and we refer you to it here. Although we'll discuss it more in depth later on in this lecture. In general, there are some lessons you can take away for testing for SQL injection vectors and discovering them. 1. Isolation stripping, that process tells you what is being filtered. You can perform this before and after discovering a SQL injection vector, and certain limitations of the vector, once you reverse engineer it, especially if it's a second order one, may change the results of your isolation stripping tests. Next, test and extract your data with the results of your isolation stripping testing. In other words, don't let your extraction process be hindered by getting filtered out by characters you've already found that are filtered out. 3. False negatives in pen test reports, especially in SQL injection, are really harmful to the industry and really harmful to your customers. And this is going to be common for pen tests that simply rely on vulnerability scanners. Do not rely solely on vulnerability scanners. You should be able to manually dive in to discovering and testing the vulnerabilities on any vector for a given target if you're in penetration testing. Next, we'll cover what you actually do once you discover a SQL injection vulnerability and how to figure out the topology of the backend database, enumerate what tables there may be, map out what their attributes may be, what the columns are going to be, and how to basically get around. So, after you initially discover a SQL injection vector, you want to discover 3 things. You want to learn what the database server software is, whether it's MySQL, Oracle, PostgreSQL, Microsoft SQL, or etc. What version of the software it is. And then you want to discover what the database users are, what their permissions may be, how many databases can each user access, and finally, you'll want to map out the table names, each table's columns, and schemas. So, there are some tricks you can use to fingerprint what software is providing the database. Specifically, version open close parentheses is a function that is provided by MySQL and PostgreSQL. Therefore, if you can inject it and it runs, and you can extract that information either in band or out of band, then it is either MySQL or Postgres. Instead, @version is a SQL variable that is basically whatever version prints that is shared by Microsoft SQL and MySQL. And this combination of features allows you to precisely fingerprint whether or not something is MySQL, PostgreSQL, Microsoft SQL, and finally, the third point I should have put is that Oracle supports neither of these. So if neither of these features work, then it is Oracle. So that's explained right here down below. If both injections are true, then the target is running MySQL. If both injections are false, the target is running Oracle. If the function test returns true, while the variable test at add version returns false, then the target is running PostgreSQL. If the function test returns false while the variable test returns true, the target is running Microsoft SQL Server. For blind vectors, it is still testable. One way to do it is injecting a clause, conditional clause, and either the function test is not null or the variable test is not null. Additionally, this is discussed further on our blog at howto.hackallthethings.com in our blog title, Blind SQL Injection Testing and Fingerprinting. So next, you want to grab the table names, and most SQL databases have a table in each database called information_schema. It always contains very interesting information. It will differ per database type, and with this table you can grab all the table names and all the column names from the database. And once you know the database type and version, this information is very easy to determine. There are cheat sheets and etc. Now we have an example below that will work for, say, an in-band append-based SQL injection vulnerability for a target that's using MySQL, and say for a 1, group concat of table name, the ASCII code for period, column name, which this operation will obtain all of the table's columns and return them as a single row that will be for every table dot column, all in a comma separated list. 3, 4 from information_schema dot columns, where the table schema is given by, say, the database. Yeah. Next, we're going to cover the details of exploiting in-band SQL injection vulnerabilities. So error-based and append-based. And again, we've covered this inserting a syntax character to trigger a SQL syntax error. It may tell you also, this technique may tell you the database version based off nuanced responses. The problem with that approach is errors are logged and error messages have smaller size constraints than data sets. But if verbose errors are on, there are multiple examples for exploiting them. Extract value function and XML update function routines disclose query results and error messages. So if you can trigger a syntax error in whatever you're trying to pass to extract value or XML update, it will spit out in the syntax error whatever it was passed as an argument to these two functions. So for an example, where we have ID is the vector here, and we're passing it extract value, and inside that is concat of 5C ASCII, which is backslash, version. And version will execute and will return a string, and will concatenate them, and it's not a valid object to extract values through, so the database will spit out a syntax error such like xpath syntax error backslash and then the version of the database, and it doesn't necessarily need to be a backslash character or necessarily have to be concat as far as I know. I may be wrong, but nevertheless, version here is the payload, and this is an example of exploiting the verbose errors. The limitation of this approach is that there's often a upper limit on the number of bytes that you can extract through these syntax errors. For instance, in MySQL, the maximum length of return data here is 32 bytes, and it'll be 31 bytes after the backslash here is used to, it is used to force the XPath error. And this will only work when verbose errors are enabled and PHP displays the error messages. So that's two things that have to go wrong. And finally, at the end, for other databases, for Microsoft SQL and PostgreSQL, we have provided examples below with cast that work in invalid casts, and they should spit out what part of the cast went wrong, spitting out the argument here to the attacker. And this is why you disable verbose errors. You should not be showing syntax errors and other forms of errors to users, ever, period. They should be filtered both at the MySQL level as well as the web server and PHP level. So next, exploiting in-band append-based SQL injection vectors, or otherwise called union-based SQL injection vectors. You must remember that all queries in a SQL statement that contain a union operator must have an equal number of columns on the left side as well as the right side. In formal speak, it must be an equal number of expressions in their target lists. So for A union B, both A and B must have the same number of columns. So using this, the very first thing we want to explore is how to enumerate the number of columns in a table. And there's a very straightforward enumeration technique where, say, ID is the injection vector, and you union it with select all from 1, select all from 1, 2, select all from 1, 3, 1, 2, 3, and selecting absolutes like this will return these absolutes in any SQL database. And this is MySQL, so we have it followed in the end by a comment meta character, which will comment out whatever the rest of the query may be in the vulnerable MySQL. And what this will do is it will return errors every time until you've guessed the correct number of columns. And it will be unioning it with the left-hand results of the query you're injecting it into. So you're guessing the number of columns in that target or that result set. So eventually this way you will enumerate and get a valid populated web page back if you guess the correct number of columns. And so in this example in the slides, the vector that you're injecting to requests 4 columns, whatever table is requesting, and it will return a valid web page when you guess the correct number that you're unioning it with. And so this will work to map the given vector even when SQL error messages are disabled, and you can toy around with it in this manner to reveal more about the parameters that it is requesting in the original SQL statement. Now, there's another technique without using the union select all enumeration method, and it is order by, or rather, it is through the order by clause, and it's similar in nature. You enumerate starting with 1, then 2, then 3, and so on, and you keep doing it until it no longer displays a valid page. And what this is telling it to do is to sort and order the result set for the given SQL statement that you're injecting into by the column number 1 or column number 2 or column number 3 or column number 4, and etc. And if you tell it to order by a column number that doesn't exist, say there's only 4, and you tell it to order by 5, it will cause some form of SQL error, and when that's filtered out, the page no longer will display normally. So you simply just do this enumerating until it no longer displays, and that tells you you've hit the number that's out of the column number range. And it's worth noting that this technique works on all the common database management systems: Oracle, MySQL, PostgreSQL, and Microsoft SQL. And it's sometimes possible to do this with group by. Yeah. The next thing you want to do is enumerate, or rather extract the database version, whatever users may be and what the current user is, what the version of the database software it is running, and other attributes and functions that may provide debugging or verbose information about the database management system. And so here are some examples below using the append base SQL injection. And assuming that you have an append base vector and it's 4 columns, then similarly you could extract the database software, the database title, the user that's currently logged in using the database, on the back end that is, the version number, and other attributes and debugging and verbose functions, etc. So next we're going to cover exploiting out-of-band SQL injection vulnerabilities, and both partial and full blind. The main 2 techniques that people use are primarily binary enumeration. However, but bitwise extraction is a far more efficient and covert technique that is used by the more elite pen testers. No tools, however, currently implement this that are out, but it beats blind enumeration by several orders of magnitude in terms of performance. And that is because blind enumeration, or binary enumeration, involves a massive amount of requests. And so, binary enumeration, is also called Boolean enumeration, is simply the process of injecting conditional statements into the vector to determine the value of a byte. And the limitation of these conditional statements is that they either return true or false about the given target data. And so, if you break down the value of a record into its bytes, say for a string, each character is going to take up a single byte. And so you iterate over each character, and you try to test by single true and false statements the value of that byte. So each byte has 8 bits, so that should be no more than 8 true or false questions. If it's any more, your approach is likely inefficient. So, here's an example. This example implements binary search as the method to extract the byte value. And so what we're doing is we're injecting a AND clause, and we're converting the value given by this into the ASCII integer value. And so the mid function is the same as the C substring function, and it's going to return a substring of the first argument starting at index 1 for length 1. So version will give you the version string. And we're starting here at the first character, which will be whatever version number it is. Typically it's going to be all you need. Well, not always. Sometimes the subversion numbers matter. But anyways, so you do this for any given string, and it starts at character 1, and the substring length is just 1. So it's just returning a single character. In other words, it's returning a single byte, and then converting that character to the ASCII value. And so a single byte is either going to be, it's going to be between 0 and 255. And so by asking if it is greater than 127, if the page displays, we know that the ASCII value is greater than 127. If we know that it is not displayed, it is less than 127, which splits that state space in half. And so if it returns false, you can go to the lower half. And then your next injection may look like this. Convert to ASCII the substring of the version string, starting at character 1 for length 1, and see if that is, for this lower half, which the midpoint would be 64, if it's greater than 64. If it's greater than, if the page displays, you know that it's greater than 64. If it does not display, it is less than 64. And this allows you to implement the binary search algorithm into your enumeration attack. And once the value for that byte has been identified, you simply increment the position argument here in the mid parameter and iterate over each character of the string. Now, this obviously takes a large amount of attempts to extract a single row of data. If you want to extract an entire table or a large number of rows from a given number of tables in a database, it's going to take a significant amount of attempts and also a significant amount of time. Threading can't help this. Vast majority of tools that implement binary enumeration do not use any threading. Some people homebrew their own stuff, and that's cool. The problem here is that this is an extremely noisy technique. It will set off all the IDS flags if they are set up properly. And by that I mean the intrusion detection system sees the traffic. So that means you have your HTTPS set up all right. You're not ignoring all attacks that come in over HTTPS. And we'll discuss that in one of the next lectures on certificates and HTTPS. And you have the IDS looking for this type of attack. So if stealth and evasion is a objective or priority, bitwise extraction is a far more efficient and advisable SQL injection technique. Obviously, we're still talking about out-of-band vectors. And bitwise extraction is the process of, instead of using conditional true and false statements, it's the process of using mathematical statements. So bit shifting or division and modulo to extract the bits of a given byte. You'll still have to iterate multiple times for a single record, but it takes several orders of magnitude less queries per byte, and thus per record. And so we've put together a blog post on some of our innovations here. We are releasing a proof of concept tool called Hack All the SQL. It's a Ruby tool, and that will be released with the launch of our SQL injection professional workshop, which has certification on attacking all forms of SQL injection for MySQL, Microsoft SQL, PostgreSQL, and Oracle SQL database management systems, as well as certification for implementing and patching, implementing parameterized statements and patching vulnerabilities. But I digress. So this blog post that we have released is a rather long blog post explaining the the bitwise extraction algorithm and how it can work in a full-blind SQL injection vector. Again, a full-blind vector is one where you cannot control the output or the data of the web page. You can only control the response time. So it's very limited, and therefore the premise of this entire approach is using mathematical queries to convert the bits of the target data's bytes or chunks, if you break them up into non-bite-sized chunks, if you just break them into chunks, converting those bits into a number and passing that number to a sleep argument, and then measuring the response time and doing this iteratively to extract all the bytes for a given record, and then piecing it all together on the attacker side. So we have infographics, we have explanation of all the timing factors and all the constraints you have to pay attention to, and how to implement it in such a way that it works even across a large network, including the internet. And we have more infographics on how the underlying algorithm works. And we have proof of concept math showing the results for every single round. And finally, we have a video showing our proof of concept tool, implementing it. It's a 45-minute video. You should not watch it all, but watching even a small amount of it will show you effectively what type of SQL injection statements it's injecting. So we have a very verbose proof of concept that shows you in a nice professional manner all of the queries that it's injecting and all of the results. And so it will automate the vulnerability discovery and then automate some of the environment mapping and discovery. And so it takes a while for it to discover the database timeout, but once it does, it begins injecting div-mod oriented queries to extract the bits through the vector. So it's building an extraction table which is a data lookup technique that's outside the scope of this current lecture. We covered in our workshop. And then it begins to extract information about the database, such as the database software, title, string, and you can see the main things that are changing are here, the division value, and then the next round changes the iterator here, and it's extracting chunks or bytes here in simply 3 queries. Now the version that we will be releasing is going to be multi-threaded, and so much of this will be run concurrently. Let's get back to the lecture. So again, partial blind is a vulnerability class where an attacker can only change the output of the page slightly, perhaps only within the original allowed results. And full blind is when the only thing you can change about the page is the response time itself by injecting sleep statements. Now we've talked thoroughly about the offense and the pen testing side of this problem. Now it's time to talk about the defense of web servers against SQL injection. Primary defense one should implement is a standardized technique called parameterized queries. It's also called prepared queries or prepared statements. This effectively relies on using placeholders for parameters and preparing the SQL statements beforehand. The parameters are supplied at execution time, and libraries exist to facilitate the sanitization of parameters that are supplied by user input. Now, the key goal, or rather the key thing here, is that you should absolutely trust nothing from the users, especially in all cases where user input interacts with database logic or database queries. The most common library and approach is PHP's PDO, which I'm pretty sure stands for Prepared Data Objects. Here is an example using PHP's PDO. Now, first, the PDO object is instantiated here, and we're assigning it to database handler. We're declaring it as a new PDO object. You declare your connection information, the port number, the database name, user, password, etc., and an array of attributes. Most examples instantiate the attribute persistent value as false. We suggest it to be true. And here's an example of it being used. You would prepare your statement with the database handler prepare function, and wherever your parameters go would be a question mark. So the statement here is select star from article where ID is given by the parameter. And then when you want to fill in the parameters, you would do statement execute and provide the user input. Here we're using the array function and we're getting it. You don't necessarily have to do it in this manner, but however you provide the user input is passed in through an argument to execute. Then, say for the PHP side, we want to store the results of the SQL statement. We would do statement fetch, then you would access PDO fetch object, and that's where it gets cached. And then you can print out and use attributes or columns rather from the result set. And I highly recommend this tutorial on PHP PDO from the PHP manual. And if you're a webmaster and you haven't done this before, I would start there. There are several drawbacks to PDO. One, it does not have any graceful array handling. It is not compatible with any SQL in clauses. For instance, select star from article where the ID is in this, say, array range or set or list. And this is a huge annoyance for any webmaster that has to run a site that has any form of mature search functionality, say searching through, this is a big problem for local law enforcement and state governments, searching through public records, where the users are provided some form of structured query language for searching through public records. It usually allows them to search ID ranges and through arrays of possible IDs or dates and etc. And so there's a very lengthy discussion on Y Combinator that we've highlighted that shows various approaches that people use to manually implement array handling, because PDO does not support it. In fact, if you try to do array handling, it is going to cause explosive performance issues in terms of it's going to, how do I say it, cache every single result from every single row of every single result in such a manner that it just eats up all of the memory of the server if the result set is large enough. And so another thing about PDO is if you do it wrong, it will both ruin your performance and offer no security. A third drawback is auto commit is set to false by default in current stable versions of PHP. And so this is something to pay attention to if you just came through that tutorial, is that this is something that's set to false by default, which means that any insert statements that are run through PHP PDO will not commit. In other words, they won't enact. They won't commit the results. They won't update the database by default. And so you have to use, say if you've prepared the statement, you've just done statement execute, you then have to do statement commit like this to actually enact the changes. Other than that, PDO is or prepared statements are again the standard defense against SQL injection. Now, to revisit the problem of array handling, when you have to manually typecast and concatenate values into the query, say when you're dealing with arrays, the results in the query are not cached by the native SQL caching routines. So for numerical values, a safe way to explicitly typecast would be to cast with int, and if you're explicitly expecting positive values, then to cast it or sanitize it with the absolute value function. For strings, in PHP, you should use MySQL real escape string, and first and foremost, be aware of all of the ways to bypass it and the limitations of it and how to properly use it. Probably one of the best resources is the Stack Overflow discussion linked here. And another point is that I think this is not discussed in the Stack Overflow discussion, that this is only safe as long as the character set, and rather the character encoding in the PHP interpreter and the SQL database are the exact same. If they're not the same, then you're going to have problems, especially if they're multi-byte characters, and sanitizing multi-byte characters is a bigger problem, and it's an exploitable, or rather, in such a case, you can exploit it and bypass MySQL real escape string, and we have a blog post here explaining this process and providing a proof of concept tool to show you all the multi-byte characters that will allow this for given character sets. Well, in the end, you really should just read every post in the Stack Overflow discussion. It's one of the actual good ones on that community. So, other mitigation tips and general final tips. When you're dealing with defending and sanitizing search fields, like exploitation can lead to a DOS, especially in those large database search websites, like what I discussed, the state and local law enforcement, etc., with public records. Injecting just a percentage sign can inject basically a like clause, and can lead to the database just choking on whatever query the attacker may inject, because you can inject a query to ask for all records that are like this, and it may cause such a result set that takes forever to process and return. Next, watch out for comma characters and new lines, especially on any imploded arrays. Some other final tips: always make sure display errors is set to off in order to avoid info leaks. Set an extremely low query timeout to prevent multi-bit timing attacks. If necessary, create multiple database users and restrict each page to page-specific database management permissions for that user, effectively implementing an access control list for the different pages of the website within your DBMS. Finally, do not allow DMS users to have create trigger, create function, create procedure, or load plugin permissions, as these often are exploited by attackers to create backdoors or otherwise escalate privileges on the system. And finally, limit host operating system DBMS process user privileges. In other words, limit the privileges of whatever account the DMS runs under, prevent outside file input and output and file inclusion of the MySQL data directory, and also limit users' privileges with load file, or select, if you can, I don't think you can actually in this case, select whatever into out file. Now, it's demo time. So, for our demos, we will be using the SQL injection vulnerability sandbox that comes with our premium SQL injection workshop at hackallthethings.com. And at the top, you have a mock URL bar for the sandbox input, and at the top right is 0 for resetting everything. And finally, our configuration menu, which allows you to configure filters, as well as what type of data type the injection vector is, as well as whether or not it's in-band, error-based, second order, partial blind, full blind vulnerabilities. And this allows you to experiment with your SQL injection techniques to make sure that in the presence of filters you can still test certain vulnerabilities. And at the bottom is a debug pane, which will tell you the result of your post. Say if you trigger some syntax character, it's going to provide you introspection on the server side in terms of debug statements. And for here, we just triggered a SQL syntax error, and it's returning that to the user, which is very, very useful for someone learning these techniques, as well as trying to become a professional penetration tester. So for the first step, for discovering vulnerabilities and doing procedural testing, again, this one little tick triggered a syntax error, but sometimes syntax errors are not always shown to users. And so I've put this notepad at the bottom to remind us of kind of the sequence of meta characters and tokens to follow. Again, the escape sequence, whitespace, conditional operator, whitespace, comparison, query terminator, and escape sequence. Now, escape sequences don't always apply. They're specifically for text-based inputs, and here we're dealing with a numerical input, so we can try things like this. You don't always need the query terminator. The query terminator is important for vectors that require a fixed or limited number of responses, which we'll go into in detail in a little bit. So, if you were to have a vector that is text-based, and we'll change that here, the escape sequence will matter. And so, escape sequence for strings is a single quote or double quote. Again, the white space, and we'll do and null is null. So we'll try this, and we see that we get a SQL syntax error, and the SQL statement that's being injected is where title equals first, and see how the string escape sequences look good there, and then we have and null is null. But at the end, there's a trailing quote. Now we can try ending it with another single quote up here, and we'll hit enter. But we see that, again, this is a SQL syntax error. The reason is because these two escape sequences denote a variable, and it's set up in such a way that and null is null is not really logically followed by another variable. So what we need is some form of query terminator, and the hyphen space is a universal SQL comment character, and what this does is it comments out the rest of this, and so it allows us to play around now. And so what we can do is null is not null, and if I haven't mentioned it already, the null is null test is a nice way to do this form of testing without using any symbols. In the case of symbols, may be filtered out. Let's reset it and go to the integer-based one and see is null, and it works here too. So again, this is a nice little easy test to see whether or not it's a SQL injection vector. And you can do is not null and vary the output like that. And so we've covered procedural testing in terms of following this for the testing of both integer and text-based SQL injection vectors. And now we're going to dive into exploiting various cases, as well as information gathering, which you do beforehand.
So, the first thing you want to do when you're doing information gathering on a SQL injection vector is you want to fingerprint the database. And as we discussed earlier, you can use the version truth table method where you test for, say, and at version is not null. Turns true, so version is accepted. And then you test for the function. And this is also true. Therefore, since they're both true, they match to MySQL, and therefore the backend database in this instance is MySQL. You can use this to determine whether or not it's Postgres, Microsoft SQL, Oracle, or MySQL. Next, you want to extract the results of the version function or variable. And this brings us to actual exploitation, because to extract this value, the technique that we will use will depend on the type of vulnerability. For now, we have an in-band append-based vulnerability. So we can attempt the union select approach to figure out what how many columns there are in the SQL statement that we're injecting into, or at least the result table. And so, whoops, it should be union select 1, 2, 3. And so union will always trigger a syntax error if there are an unequal number of columns between the two target tables. And so by using this, we then get a true statement back and actual data back when we've guessed the correct number of columns. And if we say 4, it will syntax error. That was just some lag. So going back, this is how many columns there are, and you can see this not printing out 1, 2, or 3 anywhere on the page, which is often the case for a given vector. So it is often advisable to try and limit or truncate the vector's result set at least down to 0, which allows us to append in data to extract from the database. And so that's what we've done here. And now we can do at version, and we'll get back the server version number. And we can do the other one as well. It should not matter. And yeah, 2 affects the title, so we'll do it here just for good measure. Now, for error-based, the approach is different. We want to trigger a verbose error by improperly using a SQL function, and a common one that is very verbose is extract value, and we can use this, say, like this, and extract value, which expects XML notation. That's not too current user. Let's do the version. And I match my parentheses. I need one more. There we go. So, this function tells you oh, whoops, this is not valid hex. Here we go. So, this function, when verbose errors are allowed, tells you what the syntax error is, specifically by regurgitating what the inputs to it were. So, by abusing extract value, you can use it to extract other information about the database, like current user and etc. So, the reason we use concatenate here is that extract value, when it triggers a syntax error, will parse until it finds a character that will trigger the syntax error and print everything past it. So the period here is unexpected in XML notation. So we could either append a period, slash, or some other character before this to have it extract the characters that it's truncating. So that's why we use concat here. And we can use like 2f for /, and it'll print out. 5c is /. 2e is period, and so on. And that brings us to extracting the version from a partial blind vector requires either Boolean enumeration, which existing tools do, or the more advanced bitwise extraction. For now, we will start off with the Boolean enumeration approach, which you will see requires multiple requests to even extract this one piece of information, the version. And so we'll do a quick configuration, make sure we have partial blind, and see that syntax errors are filtered out. And union select 1, 2, 3 is filtered out as well. Alright, so this is partial blind. You can see the series of SQL statements below in the debug pane. The first one is the vector that we're injecting into, and then the information that we can extract through is then returned in terms of article content that already exists in the database. And so, since we're trying to extract the version, what we will have to do is do some Boolean enumeration. And we can do something like convert to ASCII, the substring of the version string starting at character 1 for length 1, so just grab the first character. And then you have the decimal value for that character. Now you can do the binary search approach, which is, say, ask if it's greater than 127, because the byte is going to be between 0 and 255, and it is not. You can then test the converse to see if it's less than, and this is then true. But there's a problem here. The less than and greater than signs, as well as the equal signs, are often going to be filtered out in any vector. So there is a universal technique that you can use here that works in all SQL databases, is the is between 0 and 127. Oops, sorry, there is no is. The between value and value. And so this lets us search the space, and we can do between 64 and 127, so it's below 64, so this is going to be true. What we could do is then between 32 and 64, so that is true. Between 40, between 50, between 60, let's go back to 50 and work down from there. 58, 54, 52. Alright, so let's go back up to 52. Between 53 and 54 is true. Let's try between 53 and 53. That is true. And there's only one number that's between 53 and 53, and that is 53. Again, you can verify that the decimal value here for the first character is 53. And then we can go and look it up. So we're looking at the decimal value 5.3 is the character 5. So this is MySQL version 5 point something. And to move on to the next character, you would then increment right here for the mid function. Again, mid is the substring function in SQL, at least in MySQL. And we're kind of cheating now. We know that it should be 5 dot something because MySQL versions are not up to double digits. So it should be the decimal value of 46. And that is true. And we can make it different to verify that it's not a false positive. Indeed, it is 5 dot something. And now you can increment to the third and do between 127 and 255, between 64 and 127, between 1 and 64, true. So it's probably not the first 20. So between 32 and 64, correct. Between 32 and 48, 58. Let's jump up to 48. So this is true. 54, 56, 55, 54, and 54. So it is 5, 54. It's MySQL version 5.6. And you can see that this is many requests that are better off automated. This whole approach is better off automated. Just to extract this one bit of information. And this is basically the procedure for Boolean enumeration. Now, for a fully blind vector, it's going to change the SQL statements and the logic of the page that we're injecting into. This same injection is not going to actually change the output between 0 and 0. See, this should be false because we know it is the value 56 or 54. Anyways, we know that it's not 0. And so we can test and null is null. And null is not null. Return the same things. And so looking through the debug introspection provided here, the vector that we're injecting into is actually the article log here, where it's saving the user agent and what article IDs it accesses. And what's being printed on the page is a seemingly sanitized version of the ID variable, and we are not able to affect it, but we see that the null is not null is popping up here. Specifically, the 1 and null is not null. So you can change this to 5, and you'll see that it's reflected here. Now, in blind vectors, you're not able to change the output on the page at all in terms of content. So you can't extract information directly through the page in terms of data. Instead, since we are injecting into the database an extra statement here, the approach for fully blind vectors is to force sleep statements and then measure the time response from the server. The PHP and web server response should be negligible, and the sleep minimum step should at least be 1 second. Therefore, it makes it at least measurable in most cases. So we can do and sleep, and we'll do the same thing. ASCII, mid, version, character 1, length 1 for that substring. And let's see. Got that closed, and we need to close the sleep. since we're cheating, we know the value here is MySQL version 5, and we're expecting a number. We can subtract. We're expecting values between 48 and 57. Well, specifically 46 through 57. So period slash 0 through 9. So instead of having to wait 50 seconds, we can subtract off 48. And hit enter. 2, 3, 5, 6. And you see that finally it responded. Now, the page output hasn't changed at all, so you have to measure this kind of on the connection level. Most browsers have a loading animation, so you can measure that visually. But no one's going to sit here with a stopwatch and do this and in any accurate format. So this is something that is an automated technique. And so then you would proceed to extract the next character, and it's a period, so it returns immediately. And then the third character, and it's a 6. And so you'll see the time for it to respond. Boom, it's there, and so on. So this approach takes a great deal of time. Most implementations implement it in a parallel and threaded manner, such that they have a list of information that they want to map and extract from the database, and they're extracting it in this manner in parallel. So now let's do some table mapping. We'll reset this to in-band and going through ID, and we'll use append-based exploitation. So we'll do limit 0 union select 1 2 3. Okay, now we'll extract through the third one. What we want to do is we want to enumerate all the tables and their columns from the information schema. So you can do table name from information schema where table schema equals database. Let's see. Voluntest.information schema doesn't exist. I think it's information schema. So I got columns. There we go. Okay. So that gets us table name. Now we want to get column names as well. However, it's likely, yes, it's in this vector, it's only going to print one result. So there is a nice trick that works in SQL, and that is group concat, which allows you to concatenate multiple variables together. And so we'd like to do table name and say the hex value for period, and then column name. And so it's going to concatenate them all in a comma separated list. And so it's going to be table name sub column name for all tables and for all columns for all the tables. And so you would get a reply like this, where you have article.id, comma article.title, comma article.body, and so on. This is a extremely efficient approach. Group concat is a very useful SQL function for SQL injection, and we can then say copy this and then show off the table mapping, because that gets us a map of the database for error-based one. So we'll delete it all. We'll go back here, and we want to do and extract value 1 comma, and let's say the group concat of This has, let's see, this has a typo. It's not extract underscore value, it's extract value. And I think we have a mismatched parentheses. And there we go. So, what we've done is we're extracting through the verbose errors produced by extract value, and to extract more of this string, because group concat returns all of your results in a single string, we're going to need to iterate through it with mid. And the verbose errors here, I believe, only allow you to return 32 bytes at a time. So we will do mid, we already have parentheses, mid, comma, 1, comma, 32. Oh, I see. It doesn't go here. It goes not on the result of it itself. We need to move mid to the group concat. So mid cat. We'll do 132 from here, and then we can iterate 32, 64, and so on. 96. Now, if you're paying attention, you'll see that what we've been doing hasn't really been changing these first records. Occasionally you'll see a new record in the middle, and you'll see this one truncate or change. So going back to 1, get title, and we'll iterate forward by 32. We'll get log, we'll iterate forward, we'll still get log, and we'll still get log. So the problem is we're not forcing the first character to be a syntax error for XML notation. So what we have to do is yet another wrap of concat, and we'll do 5C for backslash, and wrap it here. And this allows us to then force the first character to be a syntax error, and then we can iterate up and sanely extract the values. Now I should note that the third argument for mid is optional, so you can do just one, and then you've only extracted, since the string size here is always 32, and you eat the first character by forcing the syntax error for XML notation, you then know that this is 31 characters long, so we can do 32, which should be the end of article, yes, and then we can iterate forward like that, and so on. And you can iterate over this whole thing till it is exhausted. And to better show you what we're injecting, I'll bring it up here since it's kind of lengthy. So we could just get rid of the ID equals 1 and just have ID equals extract value and still trigger the syntax error that way. But the meat of it is we're extracting through the verbose error, and we're injecting a new query here, the group concat string result of the list of all the table.column options for the current database, and we're selecting this from the information schema. Specifically, you have to specify information schema.columns, and it's often advisable to tell it through the where clause to specify only those options for the current database. Otherwise, you may get table names and column names for other databases that you can't extract from. So, on top of that, we are using mid to iterate over this string result, and we're iterating by the maximum allowed extraction window, which is given by the verbose error. Typically, verbose errors only allow the extraction of 32 bytes at a time. That is the general case. So if you get 32 bytes through verbose error, be happy. That's pretty much the best you can do. Now, to get it to sanely and predictably trigger a syntax error for the string, we're appending through concat a backslash character or slash character, which will trigger the syntax error. And then finally, extract value is going to spit out, there's an XPath syntax error. We'll change this to 1 so you see the results in the given argument. Simple stuff, right? No one's should be confused by now. Now, the process for doing this on a partial blind vector is a little tricky. We're not going through extract value. We're ID equals 1, and we don't need to concatenate a slash to trigger XML syntax error. And so this select mid group concat table name dot column name is all good. However, we need to return it as ASCII and just select a single character at a time. And then we can do between 0 and 127. This is true. And just to show that there's no shenanigans, this should be false, conversely. So, to review, since you can't see it all in the same URL bar because it's a prototype at the moment, what we're injecting into the partial blind vector is a Boolean statement on the table.column name group concat list result, and we're starting at the first character for a substring of one character, so just a individual character, converting it to the ASCII value, and then we're performing a Boolean conditional operation on it, asking if it's between 0 and 127 in terms of the byte value, and it is true. So, what that gives us in terms of ASCII values, we know that the table names and the column names are probably going to be in the alphanumeric range, starting at 65 going through 122. We're also going to have the period in there because we're doing that, injecting that in the group concat. We're also going to have the comma in there because that's our iterator. So since you're iterating over this in a very cumbersome Boolean enumeration manner, probably the first thing you want to do is, for your parsing logic, check if it's the period or the comma. So the comma is 44. Whoops. 44 and 44. So it's not that. And the period is 46. And so in this manner, since you know it's what you're parsing out is going to be a comma-separated list of dot-separated tuples, you're going to have to check those two things in the first two queries in order to keep your parsing sane. You can do it the exhaustive way, starting from between 0 and 127 and searching down, but it may average out to be more efficient to outright check those things. Anyways, I digress. So, we know it's between 0 and 127. Let's do between 40 and 127, true. 40 and 68, false. So between 68 and 100, true. Between 80 and 100, between 90 and 100, false. So it's between 80 and 90 is false. Between 90 and 100 is true. So 90 and 95 is not true. So 95 and 100 is true. 95 and 97. 96 and 97. 96 and 96, false. So we know it's 97. Now, you look it up. 97 is A. So we know the very first table name starts with an A. And then you would iterate starting with 2. Second character in this list. And so on, and so on, and so on. This again is the partial blind Boolean enumeration approach to extracting data. It works here for the version fingerprinting, table mapping, and extracting all other information. I'm not going to show it off for extracting individual records because the process remains the same. Now, there are multiple ways to do these techniques to overcome the obstacles of attacking partial and full blind vectors. And we cover these in much more detail and exhaustively so in the Hack All the Things SQL injection workshop. So next we will cover second order vectors, which are perhaps the most important topic of this lecture. Here we go, ID equals 1. So as we've discussed, second order SQL injection vulnerabilities are often missed in the wild or miscategorized as blind injection vectors. Now, this is a topic that I have not seen discussed anywhere else, not on any standard community resource or other course. So this is unique to our material here today. And so when you try to do append-based testing, you get nothing back. But you do get some partial page changes. And so you may think that the column only has one, so you may think that the vector you're injecting into only has one column, but you can only get a partial blind response out of it, which is often where most pen testers and hackers stop, and they fail to explore other vectors. So let's explore error-based, because extract value 1 concat the C backslash, let's just say version test, gets us nothing. So we confirm it's not error-based, or it's not verbose errors allowed. And the problem is that it's actually working. But since it's second order vulnerability, the syntax error gets reported to the MySQL, to the PHP code, and the PHP code gets no results from this initial query, and therefore its secondary statement, select star from article where title equals blah, is passed a blank variable or a blank result. And so they disqualify this being error-based, and then they would try some form of Boolean enumeration statement. Whoops, I forgot the and. so on, and so they can test, say, by this manner, and whoops, I have a typo. The parentheses doesn't go there, it goes here. And so they would do Boolean enumeration 0 and 127, and they managed to extract information through this way. However, the way to test for second order is as follows. We want to limit the initial results, and then we want to try using in-band techniques to map the columns being selected from each secondary query, as well as figuring out what the data type may be. We're not going to have this level of introspection, so you kind of have to guess what the data type for the first SQL statements is, or for each column what they are, and only one or two, maybe more in rare cases, will be used for the secondary vector. And so you're going to have to craft, influence the database accordingly. Now, this is fairly complicated, but we're assigning ID to -1. You can do ID limit 0, but setting a negative number for most numerical variables often will make the target query return 0 results in most cases. So we want to do union select some form of string to begin mapping. So we'll do something like concat 0x27 or 1 equals 1 order. Let's just leave out the order by right now and leave in the %. Actually, let's make it HTML encoded since it's a string, and finish it with a 27. Okay, so if we resume it to 1, it's okay. Now let's make sure that this is not some false positive. Alright, our SQL injection here is working. Therefore, with this append-based technique that we've now used, we can confirm that this is indeed a second order vector. So let's recap to explain the testing technique. We wanted to limit the injection vector's results to 0 in terms of 0 rows, so we made it a negative number. You might be able to do, I have not tested this, limit 0 and get that to work as well. And indeed it does. Okay? So however way you want to limit it, do it. Then you proceed with append-based testing, or perhaps error-based testing is really going to be on almost impossibly rare edge cases. So let's just stick to the append-based techniques. So we're going to union the limited vectors result set with a select statement to just create a string that is single quote, or some conditional statement, 1 equals 1, and then a query terminator, and then single quote. Now, this then gets returned as the string result. Again, this is the test for assuming that your initial vector is returning a string. Now, it may not always be returning a string. In the case that it doesn't return a string, the approach is actually simpler. So I'm going to configure it to flip the SQL statements, and now the second statement takes in a a number. And so title equals first, and then we do a basic truncation of the result, and then we want to do union select. Again, this is in-band technique, and we want to have it return some number. So we'll do -1 again, or 1 equals 1. And it works. I think we need to get our, let's verify by making a true negative, and there we go. So probably want to put in your query terminator just for safe measure. But now you can begin mapping the columns of the second vector. So you can do order by the first column, order by the second column, order by the third column, order by the fourth column. And when you use the order by clause, if you tell it to order by a invalid column, it's going to trigger a syntax error. And in this case, errors are not returned to the user, so we get a null response, which tells us that there are only 3 columns here. Hooray! Now we can begin the awesome process of breaking out of the second vector. Union select 1, 2, and begin getting information. Since we know that there's 3 columns, I could have just done 1, 2, 3 and seen what pops where. But now we've taken this vector that the vast majority of professionals would qualify as a partial blind vector and made it a in-band vector. So now we can select, say, add version, and do group concat, say 2x2, what is period? Do 2e? 2e, and then we'll do, whoops, we want table name, column name, and we can do select from information schema.columns where table name database. I have a typo, and my typo is that it should be table schema. Boom. You can begin extracting more information, and again, group concat is a great way to extract a number of records and append them all together in a comma separated list. And to recap, let's take this and let's put it in this notepad for you guys to see. What we did is we took the vector here, which is expecting some string. We truncated it. We then injected in a union select clause to make it return the following string, such that the first 2 characters or first character are numbers. To make the secondary query, which is expecting a number, truncate that, and then we're injecting into the secondary query this union select statement, and we did the mapping of the secondary query to figure out how many columns there are. And we did that through the order by technique. And so we have 3 columns, and so the first one doesn't show, the second one shows here at the top, and the third column will show here in the body. And then in the third column, we demonstrated injecting in another query to exfiltrate more data, specifically data from the information schema table. And this is all put together to show you that you can turn some vectors that people qualify as partial or sometimes full blind into actual in-band vectors, because they're instead second order vulnerabilities. Now let's clear this notepad and reiterate the 2 testing techniques for string and number for second order. So for strings, let's delete this all. Title equals, what was it, first, and that's what it's expecting. So you would want to truncate and then do union select or 1 equals 1, and then put in the query terminator. You want to try it like that. This is assuming that the second vector is taking in some number input or some string input. So again, you want to test it with, say, a -1, and you can also test it with a string. So you want to test both this as well, and you should test also assuming that the second vector may be expecting a string instead of a number. Again, we have -1 here to truncate the number value or variable being input into the second vector or second statement. So we want to do here concat, say, a terminating escape character for string, and then concatenate it with some simple in-band tests like above. And I believe you can do this in concat. And so again, to differentiate, for when the second order expects a number, and this is for when the second order expects a string. Now for number, we want to truncate for when the first vector is a number input. You want to truncate the numerical response some manner. You can do -1 limit 0 if you'd like, but we'll just do -1, and we're going to do union select. Let's say the second order is also a number. We'll do union select -1 or 1 equals 1. Don't forget that terminator. And if you notice, it should be almost the exact same as the above. What differs here is what you put there. And so for when the second order is a string, we'll do -1 union select concat x27 or 1 equals 1. Don't forget that terminator. And I believe this works the same. So again, this is going to be the exact same, except for what you're truncating the initial vector with. And just for the sake of completeness, we document it. So this is a very useful cheat sheet to jot down. We're going to produce an infographic with a number of useful statements and tests like this, including the universal verbose error test token, and a number of other things that hack all things. So this is, again, an extremely important concept to understand. Second order injections are often miscategorized by professional pen tests as blind vectors, when instead, if exploited correctly, they can be uh, abused like in-band vectors to exfiltrate a massive amount of data for little requests. And so, that concludes our demos for this lecture. We will not be covering bitwise extraction, which allows for the efficient exploitation of blind and full-blind vectors, as that is out of the scope for this course. Today was a lot of material. I do not expect you to need to know that for the exam, but it is an advanced technique, and those interested should seek to learn more about it at our professional workshop on SQL injection. So, this lecture we covered web application server-side security and a whole multitude of issues. We covered broken authentication and session management, security misconfiguration, insecure direct object referencing, using known vulnerable components, directory traversal, and a whole lot about SQL injection. And there are many other attacks outside the scope here, such as PHP object injection, web service 0 days, CMS plugins, backdoors, which are still a big problem, LDAP injection, file inclusion, Rails mass alignment, mass assignment, and much more. And here's the problem. The average web developer, as web technology keeps increasing in complexity, is not going to be able to climb the mountain of security issues as the field progresses. So if you want to be a security literate web system administrator, you have to keep up with the security developments of each of these things. And that is why I and many other people say HTTP sucks. So there are other resources that we can refer you to. We have multiple blogs and resources on hackallthethings.com. Nets.ec, otherwise known as NetSec, not to be confused with the subreddit, has a great wiki series on web exploitation. OWASP, the Top 10 project, is also a very good resource. There are several very useful Reddit communities that have a good signal-to-noise ratio. Sysadmin is actually one that most don't know about. Black Hat is also quite good. And we tried to maintain a good community and only allow correct answers on our community subreddit Hack All the Things. Again, if you are going down this path, you should consult the reference manual for your database management system and scripting languages, especially to cover all the security aspects that you will face. That is it for today's very, very long lecture. It covered very important topics, and these are among the most exploited vulnerabilities in this lecture that result in people getting hacked.